Welcome to session 2 of calculus. In session 2, we open with a preview of calculus. This is the session that closed session 1 of calculus, a preview of calculus. In session 1, we touched base with limits and continuity, where we discovered that the limit is the fundamental concept of calculus. We used the sum to infinity of geometric series to illustrate the limit. We discovered that the limit exists if and only if the terms converge. If they don't, if they diverge, the limit doesn't exist. The gradient of a straight line graph, the linear graph, is constant for any 2 points that are determined. Consider f of x equals to 2x minus 1. The gradient is a constant 2, regardless of which 2 points are determined. The graph of f, the slope will always be constant if it's a linear graph or a straight line graph. Let's move to linear graphs and curves. When a linear graph intersects with a curve at 2 unequal points, the constant gradient becomes the average gradient. What is the average gradient? The average gradient is the general case to determine the gradient of a curve at a specific point. We will use figure 1a, which is this one, and figure 1b, which is this one, to demonstrate what the average gradient is all about. Remember, linear graphs have constant slopes. But when a linear graph intersects with a curve, which is a parabola in figure 1a, intersects with that curve at 2 unequal points, meaning at A and T. It means the gradient will be the average gradient. It means this line becomes a secant. Now, we have line AT, we have line A1T, we have line A2T. All these 3 lines have different average gradients. Now, this gradient AT or A1T or AT, A2T or any other average gradient is used to determine the gradient of the curve. It means the secant AT, A1T and AT2 are used to determine the gradient on the curve, because the gradient of curves on the curve are not constant. They differ from position to position, point to point. To determine the gradient of a tangent, you use the gradient, which is the average gradient of a secant. The average gradient is not used to determine the gradient of a linear graph. It is used to determine the gradient of the curve at a particular point. In our case, the point is t. Now, here is A1, here is A2, and there is A. Now listen to me. Through A2 and A1, or A1 and A2, from the right side of T, this is the right side. As A tends to T, as A tends to T, through the curve, the secant AT tends to the tangent PQ. The secant AT, it becomes A1T, it becomes A2T, and so forth up to T. And then at T, there is the tangent PQ. Let me now read this out clearly. As A tends to T, the secant AT tends to the tangent PQ at T. It means the secant moves closer and closer and closer. It is diminishing. The sequence gets smaller and smaller and getting closer and closer to T. T is the tangent PQ. T is on the tangent PQ. Now, as A tends to T, the secant AT tends to the tangent PQ at T. It means the average gradient of AT gets closer and closer to the tangent PQ at T through the curve. Now, let's use algebraic methods. As x2 horizontally tending to x1, y2 vertically tends to y1. Now, x2 moves from right to left to underneath A1. It means y2 also moves from top to bottom to above, or to A1. As x2 moves further to A2, then y2 also moves further to A2. And as x tends to 1, y2 also tends to 1. It means the slope is narrowing, getting closer and closer. AT, average slope, gets closer and closer to T. It tends to the tangent PQ at T. The gradient of the curve is determined by the gradient of the tangent, the limit point. When you talk of limits, you are talking of the gradient of the tangent of the curve at that particular point. It's the gradient of the tangent, it's the gradient of the curve at that point T. It can be anywhere. It can be at A2, it can be at A1, or at A itself. Along the curve, there is a variety of gradients. The gradients of a curve are not constant. And to get that gradient at that particular point, we use the average gradient, the secant line, to get the tangent gradient. If A tends to T to coincide with point T, if A tends to T to be at the same place to be one and the same with point t, then the secant, which means the average gradient, at, will be the tangent gradient at t. The same scenario occurs with figure 1b. The difference is that we come from the left. Through B1, the left side, as B tends to T, the secant average gradient BT tends to the tangent PQ at T. Now, it tends to that tangent coming from the left side. As X tends to X1 horizontally, Y tends to Y1 vertically. If we move X horizontally to be beneath B, therefore Y moves vertically to be at B1, and we move towards X1, Y also rises towards X1. It's the same procedure. Should these two scenarios, the left side and the right side, converge to a point T, it means the limit exists. Because X and X2, they converge to X1. X2 converges, tends to X1 from the right, and X tends to X1 from the left. So if the right side and the left side converge to the tangent point of the curve, the limit exists. Note, if the x value from both sides, left and right, as I've just demonstrated, tends to t and are one-sided, equal, and corresponding, the limit exists. In session 3, we are going to focus on the concept of the limit, what I've just explained. Converging from left side and from right side to a common point where the limit exists. If that happens, then the limit exists. It shouldn't come from one side. It should come from both sides. They must converge from the left to the right, top and bottom for y values. A limit exists if and only if both corresponding one-sided limits exist and are equal. Like the video, click the button and subscribe. Thanks for watching.